Good morning, everybody. So today's ECR session is Introduction to Julia. It's a fast dynamic language for statistical computing and data science. And the speaker is our Dr. Seyoon Ko. He's one of the IDRE fellows. He's an assistant adjunct professor at UCLA Mathematics. And previously, he was a postdoctoral scholar working with Dr. Ken Leng and Dr. Hua Zhao in the Department of Computational Medicine. Dr. Ku's research interests include large-scale computational methods in biostatistics and bioinformatics using parallel and distributed computing. He earned a Ph.D. in statistics from Seoul National University in South Korea, as well as an MS in computational sciences and BS degree in physics, mathematical sciences, and computational sciences. So I welcome you all, as well as thank Dr. Ku for taking his time and coming to give us the training on Julia. So it's all yours, Dr. Ku.
Hello, I am Seyoon Ko, and I will present the introduction to Julia today in today's workshop. The material today is based on Professor Hua Zhou's lecture notes, and if you want to follow along, I put the link to it on the chat. Over the years, over last 5 years, towards the end of my PhD program and during my postdoc, I was able to do a lot of nice things in Julia. One of the largest survival analysis at the time, some GPU computation, ancestral inference, and genome-wide associated studies. And I have managed many packages from our group in statistical genetics in the Open Mendel group. So I wanted to talk a little bit about Julia in this workshop session. I will start with what is Julia? Julia is a high-level, high-performance dynamic programming language for technical computing with syntax that is familiar to users of other technical computing environments such as Python or R. The project itself started back in 2009, and its first public release was in 2012. Created by Jeff Bezanson, Alan Edelman, and Stefan Karpinski Farosha, based in MIT. The first major release was for version 1.0 on August 2018, and I started using Julia around that time. The current stable release is version 1.9.3 as of August, and the aim is to solve the notorious two-language problem, where often the prototyping code goes into high-level languages like R and Python, and the production code going to lower-level language like C or C++. And Julia wants to solve that problem, so it tries to walk like Python and run like C. Here's a comparison of performance of several languages against the speed on C. So C will be the benchmark at value 1. And on the left-hand side, we have faster languages: Julia, Lua in just-in-time compilation, Rust, and Go. And they are actually faster than C in some of the tasks. And that doesn't go much slower than three times than compared to C for those languages. And we have Fortran, the compiled language, faster than C in some cases, and not so fast in some of the cases, like printing to file and those. And on the right hand side, we have interpreted languages, which can be much slower than C in some cases. And for matrix multiplications, internally they use BLAS anyway, so they don't go much slower than C. And here's the link to the details of benchmark. So we can write high-level abstract code that closely resembles mathematical formulas, yet produces fast, low-level machine code that has traditionally only been generated by static languages like C or Fortran. And it is more than just fast R or fast MATLAB. Its performance comes from features that work well together, and you can't just take the magic dust that makes Julia fast and sprinkle it on other programming languages. Here are some links to learning resources. There are nice free online courses, cheat sheet, and always the best way is browsing the Julia documentation. And there are documentations on noteworthy differences from other languages, MATLAB, R, and Python. And learning page on Julia's website shows you some of these nice links for many other learning resources. First thing we will see is Julia REPL. So if you start terminal, and type Julia, you will see Julia REPL. Read, evaluation, print, loop. It has many different modes. The default mode, given with, starting with Julia, it is just basic Julia computing environment. And typing backspace in other modes will return to this default mode. And there is help mode. Putting question mark will show you help. And you can search you can look up the documents for those functions. And I put sum, and here is the documentation of the sum function. And shell mode, if you type semicolon, it is shell mode, and you can put your shell comments in there. So I can put Unix comments in there and see what is there. Package mode, closing square parenthesis, and this is where you can manage packages. You can add packages like this for adding packages for statistical distribution. And there is search mode. You can type Control R to search what you have typed before. And with rcall packages installed, we can enter the R mode by typing the $sign at Julia REPL. Some survivor comments from there: exit or Control D to exit Julia, Control C to interrupt execution, like in a lot of other situations, Control L, clear screen, and appending semicolon suppresses displaying output from a command, just like in MATLAB. And the include function runs the source code in a Julia code file. And .jl is extension for Julia code file. So if you get stuck to seek help from REPL, we have help modes, so question mark and then function name will help you. And just like other languages, you can Google for the solutions, and there is documentations, and you can look up the source code, and there is a discourse, and ask friends is also possible. And about which IDE to use, Julia homepage may list many choices: Juno, Visual Studio Code, Vim, just working on terminal. Unfortunately, at the moment, there are no major RStudio or MATLAB-like IDE for Julia yet. For dynamic documents like homework or short research code, I recommend Jupyter Notebook or Jupyter Lab. And for extensive Julia coding, I've been often using Visual Studio Code with extensions Julia and Visual Studio Jupyter Notebook Preview installed. And nice part of Julia is package management system. I recently moved to a job for teaching Python, and yeah, telling people to install certain versions of packages is a not very pleasing experience in Python, even with Anaconda. But it is much cleaner here. Each Julia package is a Git repository, and each Julia package name and the name of repository ends with .jl. For example, distributions.jl package lives at this URL, and Google search with package names.jl usually leads to the package on github.com. The package ecosystem is actually mature now, and it still is maturing, and a complete list of packages which are required to have a certain level of testing and documentation is shown at this link. And for example, the package called distributions.jl is added with this comment in package mode as I've shown earlier, and it can be removed, although not completely deleted, but it is removed from the current environment with the rm command. The package manager, it is included in Julia, provides a dependency solver that determines which packages are actually required to be installed. And non-registers package also can be added by cloning the relevant Git repository by using the add command and then URL to the package repository. They need to be added only once, at which point it is downloaded into your local depot, which is often at the julia/packages directory in your home directory by default. And what is nice about this package management is setting a virtual environment for different projects. So for different projects, you can have different versions of packages running in that certain environment. And that is all included in base Julia installation. Any questions? Now let's get started with running actual codes. First line we run will be version info. It shows the Julia version, build info, and what platform we are running on, and if you are running on Binder, you will see that some of the environment variables that the current environment that is there that also shows up here. And these commands using pkg is loading the package into this runtime. And pkg.status will show you which packages are installed and which version. The running environment here is defined in the project toml file in the repository root location. And you can see which versions of packages are installed there. And this command shows the detailed view of what packages are installed in my default environment. So this is for the current project we are running, and this is for my default environment, and we have a lot of packages installed there. If you start having problems with packages that seem to be unsolvable, you may try just deleting your .julia hidden directory and reinstalling all your packages. And periodically, one should run update in package mode, which checks for downloads and installs updated versions of all the packages you currently have installed. We run status up here. This lists the status of all the installed packages. And you can also run it on the package mode. And here's how to use functions in package. The using command pulls all of the exported function names in the module into the local namespace. And you can check that with the whos command. An alternative is using the import command. Then the library is also loaded in, but not the function names. So the functions from the package are available only using this kind of command, distribute the module name dot the function name, or any other object name. And all the functions, not only the exported ones, are always available like this. Let's load some of the packages we will use for the tutorial. Benchmark tools, distributions for statistical distribution, linear algebra, profiling, and sparse arrays. To get the directory of specific package it can be queried by path of function. And this shows where my distributions package is. The default Julia depot, packages, then distributions, and then these are paths inside the distributions code, or the cloned Git repository. We can also call other languages from Julia. The example here will be R. The R code package allows us to embed R code inside of Julia. There are also PyCode, MATLAB, Java code, or CXX packages for interfacing with other languages. So you can install R code package like this, but unfortunately that is not available on Binder. If you try to run this on Binder, you will face some error. Then we'll load our code package. Then we will define our first variable, x equals rand n 1000. So we randomly sample 1000 numbers from standard normal distribution with mean 0 and standard deviation 1. And then we can plot histogram of it using this command. So R then the triple double quote and closing with two double quotes defines R string. And you can write any argument in here. And $sign here is for the interpolation. So this is replaced with the X in our Julia workspace. And that is sent to here. And we can see the histogram plotted like this. You can also use other packages like ggplot. Or just call R comment like this. Then what we have in X is an R object type. And to get this into our Julia workspace, there is a collect function. Then now we have a regular vector with 10 numbers. And these are real numbers, so it has floating point with 64-bit representation. This is double precision type basically. And we can access Julia variables in our REPL mode using $sign. So we can do X equals rend 5. Then enter the R string mode after loading the R code package. Oh. Actually, I have to run this in the environment. Then we can get into the R mode using the $sign. And we can pass Julia variables in REPL mode like this. This will create a Julia vector Y, which has the same value as, so we can create R vector Y, which has the same value as the Julia vector X, sharing the same memory. We can also pass Julia expression in R REPL mode. This will just create a random vector of length 5 from the Julia side, and it will send it to R side, and then that will be stored in Y. And we can put variable into our environment using rput, and get our variable into Julia environment using rget. Those are macros. If you want to call Julia within R, there is a package called Julia call. That is interfacing with R. Let's get to some basic Julia code. Let's start with y equals 1. This is, of course, an integer, and same as int type in R. And we will query type of the a Julia object like this, and we will see int 64, integer with 64-bit representation. And 1.0 would be a literal for 64-bit floating point number or double precision number. and its time name is float64. And we can use some Unicode characters in Julia. That is same as Python 3, but in Julia, more users are leaning towards mathematics and statistics. So people actually want to push using those Greek letters within your code. So some of the major packages actually do this kind of thing. So just typing Greek letter pi would give you the value stored in pi. And as you may see, this is different. This seems different from the regular floating point number because it isn't. There is a type for irrational number. And you can also use other Greek letters. Theta equals y plus pi, for example. And just typing this will make the character appear. Backslash theta, then type character will give you this character. Y was 1.0, and if we add pi, that is 4.14159, etc. And that is a double precision number. And we can also use emoji here. And that might be something different from Python. So just typing backslash colon kissing cat colon then tab will give you this character, this emoji. And you can use it as a variable. So we can assign 5.0 and then add 1 to it and get 6.0 like this. The question I got, can I type, EU asked, can I type Greek letters in Vim or Julia? Vim for Julia. I believe there can be a package for that. Yeah. I haven't used that myself for Julia, but back in the days, back in the days when I used Vim, there was a comment automatically converting something I type into some LaTeX comment. So I think that is certainly possible in Vim, and I guess someone might have already created the package for that.
Okay, thanks.
And because there is this accent character in Unicode, we can write something similar to alpha hat by typing by inputting alpha character and then that Unicode character for some accent. And for convenience, we can do backslash hat for that. For a list of Unicode symbols that can be tab completed, here's a link. And in help mode, you can type question mark and then the Unicode symbol you want to input. Let's get to vectors. to define vector of 5 zeros with the default type being double precision numbers, we can run this method so that vector of 5 zeros are assigned to a new variable x. And we can also designate type for that. So zeros and giving int type and 5, that gives you system default integer type, which is often 64-bit integer. So we have vector of length 5 filled with 0. And we can create a matrix of double precision zeros like this. Zeros of 5 rows and 3 columns. And there also is a function called once. So this will be a 5x3 matrix filled with 1. And oftentimes, you may want to define an array without initializing its values. Then the way to go is type name, and then undef, then the size of array or matrix. This gives you 5x3 matrix, uninitialized. So those values are garbage. Of type matrix float 64. The matrix of double precision numbers. Then you will need to fill the values or put other values you may find useful in that matrix later. One of the possible way is the fill method, like this. It will fill the matrix X with zeros, and the exclamation point is part of the function name, and it is convention in Julia to denote that this function changed the values of the input in place. So what is in X now has changed to zeros. And there also is a way to initialize an array to be a constant number, like this. It will give you 5x3 array filled with the value 2.5. And Julia has different types for rational numbers here. 3 over 5 in rational type. Backed by the integer values. This is also is rational, and we can add those two numbers. And the result is rational, of course. So we had 3 over 5 and 3 over 7. Then the result is 36 over 35. Now, random number generation. The rand function generates uniform 0, 1 random numbers, like in many other languages. And changing and giving the specific type to it, it gives you random numbers in certain type. In this case, float 16 is for half precision. So these are half precision numbers. For single precision, it would be float 32. And random sampling from certain range can be done by this. So the first input here is range of values between 1 and 5, both and inclusive. So it will give you 5 by 3 array with numbers between 1 to 5. And this will give you standard normal random numbers. As I mentioned, this is for range of values between 1 and 10. 1 and 10 both are included in this range. And type of this is unit range. And this will give you range from 1 to 10 with a step size of 2. The type of it is step range. And we can use the collect functions to get those values in a regular array. So if we collect this array, collect this range, we will have an array of 1 to 10. Or equivalently, we can do the ... to expand it inside the array expression to get the values in this range in the array form. And this will give you floating point numbers between from 1 to 10. Because floating point number 1.0 is exactly that value. And we can convert a vector or any other stuff to different type using the convert function. And we can change a range into a vector of floating point numbers, like using this command. We have 1 to 10 in the form of vector of floating point numbers. Now, matrices and vectors. As I mentioned earlier, this one generates a 5 by 3 matrix with standard normal values. And we can use size function to get its size in the form of tuple. It is 5 by 3. And then giving a second argument gives you a number of rows, and giving a second argument as number 2 gives you a number of columns. And total number of elements can be accessed by the function length. Now let's see indexing. Let's create a 5 by 5 matrix using the random samples from standard normal distribution. And to get the first column, we use this command. Colon for the rows and 1 for columns. Then we get everything in the first column in the form of vector. So Julia's indexing is 1 based and less value included. First row of a matrix can be accessed like this. You can see this is same as the first row of this up here. And you can get subarrays or slices of arrays using by giving ranges to indexes. this is first and second rows and second and third columns of X. We can see first and second rows, second and third columns, these four numbers. And getting a subset of a matrix creates a copy of a matrix. But for certain computational tasks, you don't want copies. In that case, you can create views. First argument, the matrix, and then second and third argument, the indices. Then it creates a view of this matrix. So this view shares the memory space with the matrix. Equivalent comment is putting the views macro in front of the expression, in front of the index expression actually. Then we will get the same thing. And then changing this Z also changes X as well, because it is just a view of the part of X. So doing this will make Z22, which is equivalent to second row and third column of X, into 0. And doing this will make Y and X point to the same data. No copy is created. And we can check that by using the pointer function. The address they are pointing to are the same. So changing something in Y also changes X. This comment fills the first column of Y with 0. Dot equal here means vectorized operation. So we are assigning this 0 value to multiple locations in Y. Then first column of X is filled with 0 now. We can create a new copy of data using the copy function. Then they point to different locations. And if you change Z, then X will not be changed because Z is copy of the data. And they are in separate memory locations. And we can concatenate matrices. And this defines 3x1 vector in in Julia. And this creates 1x3 row vector. Actually 1x3 matrix it is. And you can do multiple assignments by tuple, like in many other languages. So 5x3 matrix is created for X, 5x2 for Y, 3x5 for Z is created and assigned. So putting X and Y together in the square bracket gives you a 5x5 matrix with X and Y concatenated together. And doing this will give you 8x5 matrix because Z is 3x5 and XY concatenated is 5x5. So up here will be X, then Y, and down here will be Z. And dot operation in Julia is element-wise operation similar to MATLAB. So let's create a random matrix X and a 1 matrix Y. And then doing this, dot asterisk will do element-wise multiplication between X and Y. So getting the same values as X. And doing this is getting the power of -2 for the X matrix element-wise. And you can apply also functions in the dot representation. This applies the sine function to what was in the X matrix element-wise. Now we have basic linear algebra. Let's first create a vector. And the norm function will give you the vector L2 norm here, which is same as this. Sum of the squared absolute values applied, and then square root applied on it. And here's another vector, y, and then we can dot product on this one. For dot product, we can use single quotes to represent a transpose, and having it between the two vectors will be same as dot product. Ali asks, is sum ABS2 X just the syntax of sum, or is ABS2 a function in Julia? Nice question. So ABS2 is a function in Julia, computing the square of absolute value. And with that sum function, it applies ABS2 to values in X and then adds the values of that. And we have matrix multiplication, which is done by the asterisk operator. And single quotation mark is conjugate transpose. So X single quote B is X transpose times the vector B, basically. And there are trace, determinant, and rank. And there is a type for sparse matrices also. It generates 10 by 10 matrix with 10% sparsity. Oh, we get only 4 non-zeros. Each element is non-zero by 10% chance, and we got particularly unlucky here for F's. Dump function is like string representation in R, and it shows everything the sparse matrix contains, the number of rows, number of columns, and its internal representations. And we can convert it to a dense matrix using the convert method like this. And also you can convert a dense matrix into sparse matrix using the sparse function. Syntax for sparse linear algebra is same as dense linear algebra. Thanks to multiple dispatch, I will talk about in the next hour. And many functions apply to sparse matrices as well. Like this. Summation of the elements. It's time for a break. I will go over control flow and loops and multiple dispatch, and then let's have a short comparison between other languages after the break.
So maybe how much? 10 minutes?
Yeah, 10 minutes.
Yeah, let's get back on here at 12:30. And I heard that many people's link is not working, so leave your link on.
Okay.
Okay.
All right. Is everybody here?
I think so, yeah, you can start.
Okay. Let's go ahead with control flow and loops. Like in many other languages, it has if, else if, those keywords. And like MATLAB, we have a AND keyword. So each code block has to end with the AND keyword. So for loop looks like this. For I in I to 10, do something with the value in I, and for loop can be nested. And for loop can be written for two different indexes at the same time. And there is break comment and continue comment like in many other languages. In Julia, all arguments to functions are passed by reference in contrast to R and MATLAB. And function names ending with exclamation point indicates that the function mutates at least one of the arguments, typically the first. So sort exclamation point will sort the array in place. And here is how functions are defined. Function keyword, then function name, parenthesis, and the arguments. And then semicolon and the keyword arguments. Required arguments are separated with comma and use positional notation. And optional arguments need a default value in the signature. When calling these functions, semicolon is not required unless there is variable length arguments. And return statement is optional. And like in R, the last line of code executed will be automatically returned. Multiple outputs can be returned as tuple, like this, return, and then the return values separated by commas. And anonymous functions is commonly used in collection function or list comprehensions, like map function here. This function squares each element in Y. Function definitions can be nested and can be vectorized using the dot syntax as shown in earlier with the sign function. So my func x return sin x squared. This is a function defined for scalar. And then putting a dot here and giving an array as an argument of this function gives you the result sin x squared computed element-wise. Collection function is similar to the apply functions in R. This applies a function to each element of a collection. So map, then the first argument being a function, and then second argument being collection. We'll apply the function f to each element in collection. Or there is a do end block. This is same as this value. This is same as using this value as the first argument and then running some function and using that as a first argument of a function. So this map function, mapping the values in x to sin x squared, is equivalent to this representation. This is the first argument of this function. And then we are computing sine of this element squared. So we are doing the same thing with this representation. There also is a MapReduce function. Apply the function to the elements in this array and then add them. So this one is another operator. And that operation is performed between the results of the map and the operation has to be associative and commutative. So this basically is same as doing this thing. And here is list comprehension similar to Python. So this gives 5 by 3 array with sin 2i plus j's as the values. And one thing notable is that Julia uses column major ordering rather than row major ordering. So the result is 5 by 3. The inner index goes to columns and outer index goes to rows. Oh, not really. Here's type system. Every variable in Julia has a type. And when thinking about types, it is similar to thinking about sets. Everything is a subtype of the abstract type any. And an abstract type defines a set of types. Consider types in Julia that are number. Here is the tree showing the types of numbers in Julia. And internal nodes here are all abstract types, and on the leaf are actual types. We have complex numbers, dual numbers, real numbers. And as a subtype, we have abstract float, fixed point numbers, duals, ratios, irrationals, integers. And as a subtype of abstract floats, we have 16-bit floats, 64-bit floats, big floats, and 32-bit floats. And for integers, we have signed integers, unsigned integers, big integers, booleans. And as a subtype of signed, 32-bit integers. And as a subtype of unsigned integers, we have 64-bit, 32-bit, 16 bits. We can explore this type of hierarchy with type of, supertype, and subtypes functions. So as we have seen, this shows double precision, this shows 64-bit integer. Supertype of float 64 would be abstract float, and subtypes of abstract float would be these: 16-bit, 32-bit, 64-bit floating points, and big float for higher precision. And there is Boolean operator for checking subtypes. And on 64-bit machines, default integer bit representation will be 64 bits. So it will be true. And we can convert number to other types. And this is often same as casting for basic types. And we can create single precision vectors and then convert that to double precision vectors as shown in the earlier hour. And doing this is same as broadcasting, the dot operation here. So this also converts the single precision numbers to double precision numbers in the form of vector of floating point numbers. This converts floating point numbers to integers. And this will not work because this is not close to an integer. We need a round function first to round it to a nearby integer. But one of the key concepts of Julia would be multiple dispatch. This is in a core of Julia design, which allows built-in and user-defined functions to be overloaded for different combinations of argument types. Let's consider a simple doubling function. Gx equals x plus x. Then we have defined a method for any type. Doing this will give you double of 1.5. But this definition is too broad because some things like strings cannot be added. This does not work. Unlike Python, string concatenation is done by asterisks, not the plus sign. So this will error. Having said that, this definition, setting the type of x to float 64, is correct. But it is too restrictive because any number can be added. So this definition, setting x as number, will automatically work on the entire type tree up there for numbers. It is a lot nicer than defining each time what to do for different types. Something like this in Julia, and also happens in many other languages. It is more brief and more understandable. Methods function display all methods defined for that function. So for now, it will give you 3 methods defined above. We defined it for floating point 64. We defined for a abstract type number, and we defined it for anything. When calling a function with multiple definitions, Julia will search from the narrowest signature to the broadest signature. And which one is being called, we can check with the macro which. So with integer input, it will call the one with the argument type number, because it is subtype of it, and we haven't defined something for in 64. And we can call this function for a vector, and it will call the general definition of G, because we haven't defined something for arrays. We haven't something defined specific for arrays, but we have definition for anything. And another core concept would be just-in-time compilation. So for problem, you would write a source code, and Julia compiler will be turning it to machine code. And then inside the core, machine code will turn the transistors, and you can get the profiling result by certain commands. Julia's efficiency results from its capacity, capability to infer types of all variables within a function, and then call LLVM compiler to generate optimized machine code at runtime. Consider the G doubling function defined earlier. This function will work on any type, which was a method for plus. So this will both work. Then the first step Julia will take is parsing the Julia into abstract syntax tree. And we can see it with this macro, code lowered. And then we can do type inference according to the, and then Julia does type inference according to the input type. And that result can be accessed using the code warn type. And we can see int 64 for int input and float 64 for floating point input. And then it will compile it to LLVM bit code, equivalent to R bytecode generated by the compiler package. So this will be the LLVM bit code for integer. And this one would be for floating point input. And we can see what is generated is different for different input. We didn't provide a type annotation, but LLVM, because different, one of them were generated depending on the argument type. In R or Python, those would be use the same code for both. In Julia, they dispatched to optimize code for int64 and float64. For integer input, shifting one bit for integer is faster than adding 2 integers. So that LLVM code is generated here. And for floating point numbers, we add 2 floating point numbers with this one. That is the lower level code generated. And then we go to lowest level, the assembly code, which is machine dependent. And these are actual instructions running on the machine. And we can also profile Julia code using the benchmark tools package. And also see the benchmark, also see profiling, and check the performance. The first one includes the compile time. So we often measure the time based on the runs after the code are being compiled. And this will show you that the code above runs in 18 milliseconds on average. And profile module gives you line by line profile results like this. And the most time is spent. And the most overhead was in getting index here. And we can have a profile view using the profile view package. And to check type stability or LLVM code, we can run these codes. Let's move on to next part of the presentation. Let's get to the next folder and open the next Jupyter Notebook here. Let's just print out the system information and load the packages. And in this part, we will review some popular computer languages commonly used in computational statistics, and we will try to understand why some languages are faster than others. What are the remedies for slow languages? There are compiled languages, C++, and Fortran, directly compiled to machine code that is executed by CPU, fast and memory efficient, but longer time to develop and hard to debug. And there are interpreted language, R, MATLAB, Python. These are interpreted by interpreter, so fast prototyping, but excruciatingly slow for loops. So there are mixed or dynamic languages, often in just-in-time compilation mode, MATLAB, R, Julia, Python, etc. Pros and cons are between the compiled and interpreted languages for them. And there also are script languages, extremely useful for some data processing and manipulation. For example, PAR are very useful for string manipulation in many cases. And there also is database languages, SQL, Hive. Data analysis never happens if we do not know how to retrieve data from analysis, and that is covered in Biostat 203B courses in Biostat. So how high-level languages work? Typical execution of a high-level language such as R, Python, and MATLAB. The compiler compiles the source code to bytecode. An interpreter on each platform interprets that bytecode into platform-specific machine code. And to improve efficiency of interpreted languages such as R or MATLAB, the conventional wisdom is to avoid loops as much as possible by vectorizing code. The only loop you are allowed to have is that for an iterative algorithm is the common sense in those cases. And then when looping is unavoidable, because running loops on R or MATLAB is too slow, you write code in C, C++, or Fortran. And that is what creates the notorious two-language problem. And some success stories include the GLM.NET package in Python, in R, whose internals is coded in Fortran, and tidyverse and data table in R, use a lot of RCPP and C++. High-level languages have made many efforts to bring themselves closer to the performance of low-level languages, such as C, C++, or Fortran, with a variety level of success. MATLAB employed just-in-time compilation technology, and for R, JIT bytecode compiler is enabled by default. And Python created a domain-specific language called Python as a compiler program, a compiler system, converting Python to C. Modern languages such as Julia tries to solve two-language problem to achieve efficiency without vectorizing code. So Python, in Python, you write Julia code and compiler will turn it to machine code. And then once compiled, then machine code will run each time you call that function later. The example we will use is the Gibbs sampler provided by Dr. Doug Bates. He's a member of our core, wrote a lot of popular R packages, and then fell in love with Julia. The task here is to create a Gibbs sampler for this probability density function. And in Gibbs sampler, what we do is sample X given Y, and then sample Y given X alternatingly, and that will give you, will create a sample for this PDF. And in this case, X given Y is a gamma distribution, and Y given X is a normal distribution. Oh. What is happening? Sorry. If you write in R, it would be a function like this, a nested for loop in R. We start with empty matrices, and then start with X and Y with 0, and then we sample X from gamma distribution and sample Y from normal distribution. And then we put the sample into the return matrix. How to generate sample of size 10,000 with the thinning of 500? Did it compile? Okay. We will come back later to it. And doing the same thing in Julia would be something like this. Two argument Gibbs function. Matrix here, X and Y starting with 0. And double for loop. Outer loop is for samples and inner loop is for thinning. and we sample in Gibbs sampling or other MCMC sampling, thinning means we take the samples after running the then many iterations of sampling. So this means we are taking 10,000 samples. We are taking 10,000 samples, and we do these random sampling 500 times each time. So we get less correlation between the samples we take. Running that in R, taking 10,000 samples, taking samples after each 500 iterations, it takes 12.9 seconds on my computer. Unfortunately, this is not runnable on Binder because I could not set up both R and Julia on that binder. And if we do the same thing, after compiling one, the elapsed time of running this code is 0.12 seconds. So this actually is over 100 times of speed up. And we wrote a very similar code. So we are getting speed up with very similar coding effort. Now let's run same operations on various different programming languages to better understand how these work. And the task is very simple, summing a vector. Let's generate 1 million double precision numbers from uniform distribution and just add them up. Random package we used is for setting the seed there, and we generate 1 million numbers, and we get summation. Then the result should be around 500,000. In Julia, benchmark tools is used for robust benchmarking, similar to micro benchmark or bench package in R. First, let's see the C code. We'll use the low-level C code as the baseline for comparison. In Julia, we can easily run compile C code using the ccall function. So this is the C code we will use. Looks obvious. And we will compile it and compile this using this code, and then run it using the ccall function. And then when we run it with the benchmark tools, with the video streaming ongoing with this computer, it takes about 934 microseconds. And let's just store the result into a dictionary. This is Python-like dictionary with key value, with key and values. And let's put it in milliseconds. So it is 0.934 milliseconds on average. Now let's run the built-in sum function in R. And we use the bench and tidyverse package in R. And then the mean runtime here is 0.4. It actually is median, 0.535 seconds. 1.535 milliseconds. Yeah, actually we're taking medians for these. And if we handwrite our loop like this, it would be much slower. Median 7.92 milliseconds. And in R, there is a RCP package providing an easy way to incorporate C++ code in R. And we can do it this way. So this basically is a C++ code doing the same thing with the data types provided within the RCP package. This compiles the C++ function. And then if we run this, the median will be 922 microseconds, similar to what we did just using C. Now we have Python. Python has a built-in sum function. And we can call to Python functions using the pycall package. In this case, the Python is running on version 3.10.12. And let's take the built-in Python sum function and benchmark it. It takes 42 milliseconds on median. So R and Python, they are both interpreted language. But the performance of a simple loop using their programming language, their syntax, performance is hugely different. 7.92 and 42 milliseconds. Oh, sorry. I had to go to built-in R. So it is 1.54 milliseconds versus 42 milliseconds. So huge gap. Why is that? Because the input in R is a vector, each element having the same type. However, here in Python, the sum function has to work on a variety types of data. It has to add on numbers, strings, and all those stuff. So it has to check what type it is running on each time it is interpreted. So the built-in sum function is destined to be very slow. And using the handwritten loop, this is the Python code. And then we will take the Python sum function and benchmark it. It takes longer, 53.6 milliseconds. And then we have NumPy in Python, high performance scientific programming library, and NumPy arrays. Then it can be easily figured out that easily figured out the type because each element in an array are the same type. So if we run some function on that, we get 178 microseconds. And this is actually even faster than C results, which was at 900 microseconds. That is because of computational order here. So the code we have written for the loop is adding the numbers from the first element of the array to the end of the array, one by one. However, this one is actually pairwise sum algorithm or binary tree reduction. This gives better memory performance and better numerical stability. So this is more optimized operation for summation with the numbers having the same data type. Actually, it is on par with a Julia built-in sum function we will see in a moment. We precompile the code and then we benchmark the sum function. 181.5 microseconds, similar to the NumPy results. The built-in sum function in Julia does almost the same thing as built-in sum function in NumPy using the pairwise sum algorithm. Then let's see what happens with handwritten loops in Julia. The benchmark result is 923 microseconds, similar to what simple C loops achieved, because this is just-in-time compiled. After compilation, the runtime is similar to C code. And what is nice in Julia is that we can annotate the loop by a macro to try to accelerate this. Here is a fast math macro. It aggressively tries to do the operation quickly by changing the order of operation and automatically vectorizing code using the vector instruction as available in the computer. So it becomes faster than the simple handwritten loop. And there is another macro called SIMD, single instruction multiple data. And it tries to use SIMD instructions as much as possible without breaking or reordering the operations, because reordering operations and in this context, in this context, because the precision we have is finite, changing the order of addition actually may get different results. But for this one, the operation is actually simple enough, and simple enough to generate the same machine code as fast math. So we have the similar result. So this is similar to putting the SIMD flags for compiling the C code. And this is similar to putting the fast math flag for compiling C code. And that is all accessible in this notebook. And then we have loop vectorization. And this is a nice package, more aggressively try to vectorize and reorder the operations even more than the fast math flag. It takes a while for compilation, but it eventually becomes faster than what we were. It is faster than any other numbers what we have seen. And this macro is easily multi-threaded using the T-turbo macro. And it becomes even faster after first compilation. 46 microseconds. So here are the results of the benchmarks. The fastest being the multi-threaded version, and then single-threaded, the turbo operation from loop vectorization, aggressively optimizing the computational order and vectorization, and then Python NumPy and Julia built-in, which uses a different algorithm, pairwise summation, and Julia FastMath and Julia SIMD, which tries to use SIMD operations without changing the computational order in this case. And then we have RCPP, Julia handwritten loop, and C loop, which we have which adds the numbers from front to back. And we have Julia R built-in, slightly slower than the handwritten C loops, and handwritten R loop, which is much slower. And then Python built-in, which has to work on all the different things, 42 milliseconds, and Python loop taking 53 milliseconds. What I have to note here is that Python also has a just-in-time compilation, specialized just-in-time compilation package called Numba. And if we use that, we may get the numbers around this one And with the first math option, we may get the result around this one. So with the baseline C up here, Python built-in and Python loop are over 50 times slower than C because loop is interpreted and does not specialize in input data type. R loop is about 10 times slower than C, and that is performance of JIT bytecode generated by its compiler package. And Julia loop and RCPP close to C performance because Julia is just-in-time compiled with specialization, and RCPP and C just basically the same, almost the same thing. And Julia built-in and Python NumPy, those use different order of summation, 4 to 5-fold faster than the basic summation loop, more numerically stable, and less memory bound. However, using SIMD and more aggressively optimizing, we get faster speed than the built-in sum functions. And using multi-threading, we can get faster than that, using the top performance on this machine with very aggressive vectorization. Here's a take-home message. High-level language programmers should be familiar with existing high-performance packages, and they don't need to reinvent wheels. There are things like RCPP eigen, tidyverse, NumPy, SciPy, Numba. In most research projects, looping is unavoidable. Then we need to use low-level language in R or Python. RCPP or Python are those domain-specific languages. And Julia circumvents these two language problems. So we can spend more time on algorithm, not on juggling 2 or more languages. That is the presentation today. Any questions?
Oh, that was really good. Any questions? Just raise your hand so that you can speak. Looks like everybody learned everything. So, what are the? Let me ask this question. Suppose you have a C code or Fortran code.
C or Fortran code?
Yes, and that's one of the legacy codes. What could be the advantages of converting those into Julia?
So converting the compilation languages to Julia, the advantages would be the code will be more readable, more maintainable, and Julia has some nice, more aggressive optimization strategy in there. So we may be even able to speed up things. So this loop vectorization thing gets faster speed than C with fast math or simple SIMD vectorization in this case.
Yeah, so the takeaway is that if somebody is looking to get more, optimal performance without getting hands dirty,
Yeah.
then Julia will provide you a
Yeah,
better.
Julia can provide you a way to this.
But if you are expert in optimizing the codes at Fortran or C level, then I think it's a matter of choice.
Yeah, it could be if you're experts. It could be a matter of choice, but Julia code is more maintainable, easily readable. That is a catch here.
That is right. Yes.
Yeah.
Well, thank you very much. Is there any other questions? Please let us know. If not, let's thank Dr. Ko.
Thank you for attending.
I'll see you sometime in the next sessions. We generally have these ECR sessions every month. So hope to see you during those. And again, I'm sorry today this because of the confusion in timing. We were supposed to start at 11 or 11:30. I was confused in that. So that I take that on myself. So thanks again. And I will be posting this video on the online, and I will send out an email with the link. So thanks again. Have a nice rest of the day. Thank you, Seyoon.
Thank you.